Hi, in this video we'll talk about the Holt-Winters procedure and the methodology that's used to make an improvement on the exponential smoothing forecast. Recall in our last video we had looked at exponential smoothing in detail, looked at the code for it, the syntax, and looked at the forecast for some exponential smooth forecast data, and we saw that the forecasts were flat. And the reason that the forecasts were flat was that was the assumption that there is no trend or no seasonality in the data set, and there's just this mean level, and that's what the exponential smoothing algorithm was trying to estimate, and therefore it gave flat forecasts after the last predicted value. But in a lot of cases, it would not be accurate to assume that there is no trend or no seasonality, because in a lot of real data sets we expect that there would be. For example, temperature, we know that that cycles. So there are certainly cases where we need to consider the trend and seasonality. Another word for seasonality is cyclic behavior, and Holt-Winters does exactly that. This method was developed in 1957 by two famous economists named Holt and Winters, and I think you'll be impressed with the accuracy of forecasts that come from the Holt-Winters method. Let's go over to R and we'll run some data. I'll go ahead and erase that plot, and let's take a look. So we're going to do two different examples. The first example will be an additive example, and the second will be a multiplicative example. The first one, the additive data set, will be one that we've looked at before, Texas unemployment. Remember, there was some discussion earlier in this chapter about seasonally adjusted versus not seasonally adjusted. The data set that we're going to look at is going to be unadjusted. Recall that we looked at that in detail about seasonal adjustment versus not. We also looked at the moving average smoother on this particular data set. But now what we want to focus on are the Holt-Winters forecasts for this data set. These first three lines are all equivalent. I was just curious myself about the default here and wondering if it cared if we said seasonal equals add versus additive, or just nothing at all. And they're all the same, but let me go over the syntax in detail because it's the Holt-Winters syntax, which we've never talked about before. So we're going to say texas.unemployment.hw for Holt-Winters is given by, and here's the syntax, Holt-Winters, be sure to capitalize the H and be sure to capitalize the W. Everything else is lowercase. And then parentheses, data set name, Texas unemployment unadjusted for us, comma, seasonal equals add or seasonal equals additive or nothing at all, because that's the default. Now, why do we think that this is an additive seasonal data set? We'll see that in just a minute when we look at that. So let's run that piece. Then let's plot what we just found. That is the Holt-Winters forecast. Looks like this. Notice that the red, that's the forecast, is superimposed on top of the black, which is actual. And look how close it follows. It's really remarkable how well this Holt-Winters algorithm does in tracking the data. Now, let's talk about the additive piece. Remember, additive just simply means that the variation that you see, I'm kind of just tracing it a little bit, doesn't seem to become more exaggerated over time. So I would say that the distance between the bottom and the top, that is the trough and the peak, or the valleys and the peak, however you want to say it, pretty much stays the same. We're going to see in our next example where that's not the case, but that's why we call this additive, and that's not necessarily the point of this video, but wanted to bring that up. That's a little bit of review there. But notice how closely that tracks. It does a great job. Now, remember that that's just the that would not be something we need. If we've got the data through 2020, why do we need forecasts? And we don't. We were just wanting to show that it follows the trend. So let's go ahead and look at what would happen if we were wanting to know the next 3 years worth of forecasts. So we're going to call this texas.unemployment.pred for predict, and we will actually use that term predict for our syntax equals predict, parentheses, data set name, comma, how many ever months worth you want to predict. So run that and plot it. And when you plot that, you're going to have two different lines. You've got your original data, original meaning your Holt Winters forecast, and then you've got these new predicted values that go beyond 2020, and then we say line type equals 1:2. Let's R know that we've got two different data sets coming in here that want to be plotted at the same time. Let's run it and see what happens. So you can see what we've got. There's the data that goes through 2020, and then this red line all by itself are those forecasts for the next 36 months. That is the next 3 years. And what do we see about it? Well, we can't know for sure what the actual data is going to do, but we'll certainly say that it looks like it's following along the pattern that had been established in the time periods right before it. So it's a pretty believable looking forecast. And that's our first example. That's an additive example. Let's now go to a multiplicative example and go back to the very well-known air passengers data. We're going to call that multiplicative because, on the other hand, this is going to have data that varies quite a bit as far as like the difference between the peaks and the valleys as time goes on. So let me show you a picture of that right away. So AP for air passengers, .HW for Holt Winters equals Holt Winters, data set, comma, seasonal equals multiplicative, and let's plot it and see what that looks like. Here it is. And again, let's look at this. We'll talk about the multiplicative piece really quickly. See, early on, the distance between the valley and the peak was pretty modest. As time moves along, it begins to increase, and later on, it's pretty significant. That's why we call this multiplicative. Okay, now back to the Holt Winters piece. Holt Winters, the forecasts are in red. Notice how well they track along with the data, just like we saw for Texas unemployment. And very impressive so far. This is looking really good. Now, this time we're going to do something a little bit different. We're going to, we're going to do the same thing first of all. So let's look at what would happen if we looked at the next 3 years. So remember, this data went from, the air passengers data went from 1948 out to the end of 1960. But let's predict what would happen for the next 3 years, because we're saying n dot ahead equals 36. So that means the next 36 months. So we say AP.pred for predict equals, here's the syntax, predict, parentheses, data set, that's AP.HW, and then comma, n dot ahead of 36. So that's the next 3 years worth of data. And then let's plot that. Again, we'll use the line type 1-2, and we're going to plot the Holt Winters, and then along with these new predicted forecasts. Let's run that and see if it also seems to hold the pattern as we would expect. And it does. Remember, the data set went from 1948 up through 1960, and then at that point, we dropped these forecasts in. And these forecasts went for the next 3 years and look like this. And again, it certainly looks like it extends the pattern that had been established in the past. Again, Holt Winters looking like it's doing what it's supposed to. Now, here's the only thing with this. We're talking about assessing forecasts and how good they really are. This is just a conjecture. This is just a guess. We think that's what's going to happen. Just based, our eyes tell us, yes, you followed the pattern that looks like had been established before. Well, really, you can't truly quantify that. And you can't know for sure how good that is. So a better way to do it, in a way that's often used in practice, is to have this training data set and this test data set to where you actually test real data values, actual data values, with some predicted values. So what that really means is you would like to take this entire data from 1948 to 1960 and let a certain amount of it, designate a certain amount of it, let's say 70% of it or 80% of it, to be your training data set, and then let the remaining piece, whether it's 30% or 20%, be your test data set. And that's exactly what we're going to do here. So you'll see that what we're going to do is we're going to make this window. We're going to call this AP9, and that 9 really means we're going to look at 9 years worth, not 12 years worth. We're going to let 9 years worth be the training data. We're going to start it at 1949 and end it at 1957. So we're going to chop it off 3 years early. And then what we're going to do is we're going to let Holt-Winters use the Holt-Winters syntax on AP9. Seasonal equals multiplicative again for the same reason it was before. And let's look at that. So remember, it's going to look a lot like this. It's just going to be chopped off. So let's run this. And let's plot. And so here's what we have. You can see that what we've done here is we've looked at plot air passengers. That's the actual data, type equals L. And then we put on this part about the predicted values. So we go from 1949, that is, up through 1957, right? That was the actual data. And then what we do is we look at these predicted values, which were predicted on a portion of the data where we have the actual values. And that way we can see how well that it would have done in an area where we knew the true answer. And we can see that it does a pretty good job. It doesn't quite track the peaks as highly as they really do exist. And notice that for the lows, it goes down a little bit lower than it actually does. But hey, that's more realistic. We weren't expecting this to be perfect, but we're still convinced that this Holt-Winters method is doing what it's supposed to do. So that's the Holt-Winters method. You see that the syntax is really quite easy to work with, and that's an advantage. One thing I didn't mention is that so what did Holt-Winters do in order to make this work out? As I said, we're convinced that it works. It looks really good to us. It's doing a great job of tracking and making forecasts into the future. But how did this come about? Well, recall the exponential smoothing forecast. That was an iterative algorithm formula, right, that looked at previous time points. It depended on the parameter, the tuning parameter alpha. Alpha ranged from 0 to 1. And that was to estimate the mean. But remember, we've got a trend and a cyclic component coming in. So Holt-Winters said we need to add 2 more equations to this to estimate the trend and to estimate the cycle. That is the seasonal component. So instead of just being alpha, there's a gamma and a beta. And this thing is a more complex set of equations, and you can see that in the text, and you can see in the text that we comment that it's a very difficult thing to understand, and we don't necessarily get into the depths of the formula and do what we did with the exponential smoothing, but it's really a complex set of equations that apparently work quite well. And the good news is that our syntax, Holt-Winters, takes care of that calculation for you. It does its own estimation of the parameters, those tuning parameters. So it's very handy and good thing to have in your toolbox. So be sure to use the Holt-Winters algorithm.